When we started our section on waves, we said that energy was transferred along a wave. Here's a video of somebody doing a rope workout. I've never done one of these myself, but when I talk to people who have, they say it's a really hard workout, and I can totally see that. To make those heavy ropes go, you have to put a lot of energy into it. So we definitely know there's energy transferred. How do we find the energy of a wave on a string? We know very well that waves do have energy. When you stand in an ocean wave that hits you, it can knock you right over. The sun on your skin warms it nice. If you're in a concert with really loud sounds, you probably even feel the vibration in your body. So let's start by asking, if we have a wave on a string and the wave is produced by simple harmonic motion, do we know the total energy of an object moving with simple harmonic motion? And I think we do know that. That energy is kinetic plus potential, and that's a constant value. So it alternates back and forth between kinetic and potential. Sometimes it's a mix of both, sometimes it's all kinetic, sometimes it's all potential. So if U is equal to 0, then K is equal to a maximum, which is equal to 1/2 times M times V maximum squared. Okay, so let's apply this to our wave on the string. So let's look at our wave on a string. Let's pick a little piece of that string, so an element of the string, and let's say that that element of string has mass that we'll call delta M. That delta just means a small bit, and it has a little bit of length that we'll call delta X. So I'll label in my delta X, that's how long it is. And the motion of that string is that it goes up and down with simple harmonic motion. That's the kind of waves we've been looking at so far. So our element of string with length delta X and mass delta M, moving with simple harmonic motion, has an energy that we can write down. That energy is 1/2 times delta M times V maximum squared. So that's when it has all kinetic energy. Well, what do we know about V maximum? We know that V maximum is equal to A times omega, where A is the amplitude of the wave and omega is the angular frequency. Let's put that in our expression. 1/2 times delta M times A squared times omega squared. A and omega are squared because V was squared. Okay, what can we do about that mass? Let's remember mass per unit length. So mass per unit length would be delta M over delta X. That tells me that my little bit of mass, delta M, is mu times delta X. So the amount of mass in that little bit of string is the length times the mass per unit length. I'm going to put that in my expression next. So I've got 1/2 times mu, the mass per unit length, times delta X times the amplitude squared times omega squared. Okay, this is the expression for the energy of that little bit of string. That can be useful, it's kind of okay, but power, the rate of delivery of the energy, is a really useful concept. So let's switch to power. Let's ask, what's the power of that wave? So how fast is the energy delivered? That's really important. So the expression for power is change in energy over change in time, the rate of delivery of energy. So we're going to take the derivative of the expression we just found for energy. Now, everything in this expression is a constant except delta X, because delta X moves along the line. So everything comes out front except delta X. So I'm left with 1/2 times mu times A squared times omega squared times the time derivative of position with respect to time. Well, position over time, that's speed, and that's the wave speed. So our expression for power delivered by a wave. I ran out of space a little bit, so I'm just going to move up. Hopefully you can still follow it. Power is 1/2 times mu times a squared times omega squared times v. This is power of a wave, or the rate of energy transfer of a wave. If you printed off the pre-class slides, you would have noticed this example in there. I decided to make up a new example instead and ditch this one. So you can forget this slide ever existed and we'll move on to the next slide instead. So for our example of power, let's go back to our geologist example. So we had a 2-kilogram rope that was 80 meters long. It was stretched taut by a 200-kilogram box of rock samples attached at the bottom. The geologist made a wave on the rope. We were given that the frequency of that wave was 200. What we did in our previous example was we found that the wave speed was 280 meters per second. Now I'm going to say if the wave created by the geologist had an amplitude of 5 centimeters, so pretty small amplitude, how much power was delivered by that wave? Let's write down our power equation. Power is 1/2 times mu times a squared times omega squared times v. Let's see what we have to put in for each of these terms. So we've got 1/2 times mu. Let's remember that mu is the mass per unit length. It's the mass of the rope divided by the length of the rope. So that's 2 kilograms divided by 80 meters. Now, if you wanted to calculate that first, you certainly could. I'm going to go ahead and write it all out in the equation. A means the amplitude of the wave. That's 5 centimeters, but we'll convert it to meters. 0.050 meters. Times omega. Let's remember that omega means the angular frequency, and that's 2 pi times the frequency f. So I've got times 2 times pi times 2 hertz. That whole thing has to be squared. Then I'm also multiplying by the wave speed, which we found previously to be 280 meters per second. Put all that through the calculator and we get the power delivered by that wave is 1.38 watts. This example is similar to the previous one, maybe just a little bit more in depth. So we have a wire stretched with a tension of 94 newtons. Tension has a symbol of F. The speed of the waves is 406 meters per second. We want to know what is the amplitude if the frequency is 68 hertz. And the power is 0.365 watts. Let's start with our equation for power. 1/2 times mu times a squared times omega squared times v. Right off the bat, this looks a little trickier because we don't know mu. So what are we going to do about mu? Let's remember that wave speed is the square root of the tension divided by mu. So v squared is f over mu. So mu is f over v squared. Let's put that in our equation. Power equals 1/2 times f over v squared times a squared times omega squared times v. Here we notice we've got a v on top, a v squared on bottom, so one of those guys cancels. We're asked to find the amplitude, so amplitude squared is going to be 2 times the power times v divided by f times omega squared. So amplitude A is going to be the square root of all that business. Okay, now we can go ahead and put our numbers in. So we've got 2 times the power, 0.365 watts, times the wave speed, 406 meters per second, divided by the tension, 94 newtons, and also divided by omega squared. Got to remember that omega is 2 pi f, so 2 pi times 68 hertz, and that's squared. Why don't we even get that in our notes up above? Omega equals 2 pi f. And don't forget to take the square root of everything. And what we get for our amplitude of that wave is 4.16 times 10 to the minus 3 meters, or 4.16 millimeters.